Hello, this is Dr. Christy Patton-Lukes, a chemical engineering professor at Missouri S&T. We are continuing with our studies of absorption and stripping in this lesson. And what we were last talking about was the rate of absorption, and that we have a lot of different ways we can write this. We can write it in terms of the difference between the Y in the bulk gas and the Y at the interface, or the X at the interface and the X in the bulk liquid. Or we can do it in terms of the Y in the bulk gas and the Y that would be at equilibrium with the bulk liquid, or the X that would be in equilibrium with the bulk gas and X. And the choice of film coefficient or overall mass transfer coefficient is based on what we choose as our driving force. And then we talked about how we can estimate the interface composition by comparing the first two rate expressions and coming up with an expression for the slope of the line from the operating line to the equilibrium curve, and that will be a line of slope with negative kx over ky, because you'd want this as y minus yi over x minus xi. If the equilibrium curve is straight and the operating line is straight, then we can do the integration and estimate it as straight lines, and we end up with these expressions here. And you could do that with any of the various forms, but this is for the overall. And then we had a bunch of formulas, and this is just a selection of the most commonly needed ones. But again, they are based on whatever your driving force is. So how can we use this to actually do the calculations? It depends on whether or not you have film coefficients, kx, ky, lowercase, or overall mass transfer coefficients, the capital K, x, or ky. So let's look first at the film coefficients. The first thing you want to do is plot the operating line as a straight line on the same graph with your equilibrium data. Then you need to find estimates of kya and kxa. And we're going to use these to estimate the slope. And that slope, as we just saw, is going to be negative kxa over kya. Now then, go to your operating line and select points along that line. From each one of those points on the operating line, draw the line with slope negative kxa over kya. Where this intersects the equilibrium curve is going to be the point xi, yi. Now then, let's say we're going with ky, then I'm going to need to read the points y and yi from the graph. Y comes from the operating line. Yi comes from the equilibrium curve with these little crazy slopes. If you are needing to do this in terms of the liquid phase, then you're going to read x and xi from the graph. Next, you want to estimate h sub y or h sub x, whichever is appropriate. And so you can either, if you assume that everything is straight lines, then you can use the estimate of delta y log mean or delta x log mean for h sub x. The other choice is that you're going to need to numerically integrate these integrals, dy over y minus yi, or for h sub x, it's dx over xi minus x. Our last step then is just simply to figure out what h sub y and n sub y are, and then estimate z. And this should be n sub y. And that's going to be wrong on the next slide too. Now if you have overall transfer coefficients, this actually becomes easier because you still start with finding your equilibrium data, and on the same graph plot the operating line as a straight line. But next all you do is you read y and y star from the graph. So they're just going to be straight up and down from each other. For a particular y, you look right below it, that's y star. If you're working with x's, you're going to read the value of x and go straight across the same value of y, that's going to be x star. Calculate your delta y or delta x log mean, and then do your integral. And then multiply HOY and NOY to get z. And again, remember, I said that this is supposed to be an n. So in our next video lesson, we're going to look at solving an example problem for absorption. But first, let's talk briefly about how is it different for stripping. Okay. So desorption or stripping is going to be essentially the same, except that the operating line is going to fall below the equilibrium curve. Okay. So almost the same. Typically, for the case of stripping, what you have is you have a contaminated liquid and you're going to bring in a clean gas to strip the material from the liquid. And so you're going to know the liquid flow rate, you're going to know the composition of the liquid at the inlet and what you want it to be at the exit, and you should know what the composition is of the gas feed. You're going to then be wanting to work with a driving force. Normally, in this case, you normally work with x's, and the operating line will be to the right or below the equilibrium curve. We're going to plot what we know and then vary our slope so that we wait until we see how long it takes before we get the unknown. Okay, so what you have is you know what's coming in the liquid at the top. You know what's coming out the liquid at the bottom. You know what's coming in the gas at the bottom. So what's going to vary will be the top of the tower. You don't know what the gas will come out like. And so you're going to vary that until it just touches the equilibrium curve, looking for a pinch point. This graph is not particularly awesome for seeing that. But you're going to be able to do the same kind of thing that we did before. That'll give us a limiting case, and then we'll choose a V that's larger than that, usually on the order of 1.4. One last topic I want to talk about is what happens if you're changing your temperature and pressure. It's not going to affect the operating line so much as it affects the equilibrium data. This is going to change your driving force. Your driving force is this delta Y or delta X. It's the mole fraction difference. So on pressure, increasing pressure is going to increase the mole fraction of the driving force, which reduces the number of transfer units, the NX or the NY or whatever. If you are maintaining a particular number of transfer units, then you can decrease the liquid flow rate when you have higher pressures. Now for temperatures, what's going to happen is generally the system is not ideal, and so there's some heat of absorption or heat of solution, and this will in fact cause the temperature to increase. So that's the reality of this. But when you evaporate your solvent, that's going to decrease your temperature. Frequently, these two phenomena kind of offset each other a bit, but usually the heat of absorption or heat of solution is the larger, more dominant effect. So normally what you're going to notice is that the liquid temperature will increase as it passes through the tower. If this is actually a significant phenomenon, then you must complete a complete mass and energy balance through the column. Now we're going to be leaving that to like Aspen or other process simulators to evaluate those, but just be aware that this is a serious concern, especially for our very non-ideal solutions. So in our next examples, we're going to look at an absorption tower, and then we will look at a stripping tower when we have linear operating lines, and then we'll begin to look at what happens if our equilibrium curves are not straight lines, if I can't use these simple approximations using delta Y, log mean, etc. Thank you very much for your time.